Yes, sir.
Chopde,
Yes,
right?
sir.
Rutvik Gune,
Present, sir.
okay. Sadashiv, right? Sagar, Sai Prakash,
Present, sir.
Sai Prakash,
Present, sir.
okay, right? Samir Ahmad,
Present, sir.
okay. Sania,
Present,
Sania,
sir. Present, sir.
right? Sanjay, okay. Sanjay, Sanjay, Sankalp, Sanket, Shiraj,
Present,
Shiraj,
sir.
okay. Shunanda Natikar, Shraddha, Shraddha,
Present, sir.
right? Shubham,
Present, sir.
Shubham, okay.
Present, sir.
Sumit, right? Sumit, Sumit, Suraya Banu,
Present, sir.
Suraya Banu, okay. Tejas, Tejas,
Present, sir.
right? Vivek, Vivek, Yamanappa, Yamanappa, गांवकर रजत रामचंद्र, गांवकर रजत रामचंद्र,
Present, sir.
ओके. मंजुनाथ मिल्लीगिरी,
Present, sir.
राइट. प्रथमेश,
Present, sir.
ओके. जोसलिनो, जोसलिनो, सोहम, सोहम, अतिया,
Yes, sir.
right? Anybody else joined?
Sir, roll number 13.
Janvi, sir.
Janvi,
32,
13,
sir.
Ratan Birje, 13, 1 minute, Janvi, Ratan Birje, Janvi, 32,
Yes, sir.
30, 32, Vivek Goni, okay. Anybody else? Right. In the last class, we had started with the multi-stage amplifiers. Are you able to see the screen? Screen is visible?
Yes, sir. Yes, sir.
Right. We saw the cascaded systems. What are cascaded systems? They are connected in cascade. Output of one stage is connected to input of next stage. The total gain will be given by the product of the gain of individual stages. Is AV total is equal to AV1 into AV2 into AV3 if there are three stages. If there are three stages. Next, let us see cascode connection. Cascode connection. In the cascode connection, as I told in the last class, that the common emitter amplifier drives the common base amplifier, or the output of the common emitter amplifier is connected to the input of the common base amplifier. This is called as cascode connection. Output of the common emitter amplifier is connected to input of the common base configuration. Okay. Now, in this cascode connection, the input impedance is very high, input impedance is high, and the output impedance, the final output impedance of the common base stage is also high. The input impedance of the common emitter amplifier, this is common emitter because emitter is common between input portion and the output portion. This is common base because the base is common, base terminal is common between input section and the output section. The input impedance of the common emitter amplifier is high, and also the output impedance of the common base amplifier is high. The input impedance of the common base amplifier is less. Input impedance of this common base amplifier is less, which loads the output of the common emitter amplifier. So this is just acting like a load now, because the input impedance of the common base stage just acts like a load to the common emitter amplifier output. Yes or no? The input impedance of the common base amplifier acts as a load resistance, it acts as a load for the output of the common emitter amplifier. Then here the capacitance at the input of the common emitter amplifier or at the input of the cascode connection is less. Because of low value of capacitance, we know that Xc is equal to 1 upon 2 pi Fc, right? Xc is 1 upon Xc is equal to 1 upon 2 pi Fc. We know that Xc is equal to 1 upon 2 pi Fc, or C is equal to capacitance is equal to 1 divided by 1 divided by 1 divided by 2 pi 2 pi 2 into pi 2 into pi. Okay, Xc is 1 upon 2 pi Fc, or C is equal to 1 upon 2 pi 1 upon 2 pi Xc 1 upon 2 pi into F into frequency. Okay, so because of the low value of capacitance is less, capacitance and frequency are inversely related to each other. As the capacitance is less, frequency will be more. That means this cascode connection amplifies high frequency values. The cascode connection amplifies high frequency values or high frequency input signals because it is having low value of capacitance. Therefore, as the capacitance is less, frequency will be more according to this relation. Xc is equal to 1 upon 2 pi Fc. Then as the frequency is more, it means that the cascode amplifier can amplify high frequency input signals. This is the one of the features of the cascode connection. This is one of the features of the cascode connection. Okay, so such feature is may not be present in another types of amplifiers, that is common base and common collector amplifier, but in the common this cascode connection or the common emitter amplifier, as the capacitance is less, its frequency is more. That means it can amplify high frequency input signals. In cascode connection, the output of common emitter stage drives the input of common base stage. That is, cascode connection has low input capacitance. Because of this, it can amplify high frequencies. This is an advantage of the cascode connection, that it is having low input capacitance. Because of the low value of input capacitance, it amplifies high frequency that is possible only with the common emitter amplifier. Then cascode connection has high input impedance, as I told, provided by common emitter amplifier, and high output impedance provided by the common base stage. So this is our cascode. Just have a look at it. Common emitter is common between input and output. Then base is common between input and output. Here, common emitter amplifier output is connected to the input of the common base stage. The frequency response of the common base stage is good, or it is having high frequency response. Frequency response means it is the plot or the graph of the gain versus frequency, or it is a plot of output voltage versus frequency. If we plot the graph of output voltage versus frequency, the frequency response is good. That means the bandwidth is good. Whatever we are obtaining, it is nearer to the manufacturer given value. The bandwidth of the common base amplifier or the cascode connection, right, it is nearer to the bandwidth provided by the manufacturer. It is having good frequency response or high frequency response. The low input impedance of common base stage loads the output of the common emitter stage. That's what I told. The common base stage input impedance is less, which acts as a load to the output of common emitter stage. Voltage gain of common emitter stage is less. The voltage gain provided by the common emitter stage is less, whereas the voltage gain provided by the common base stage is high. Suppose say the voltage gain of common emitter amplifier is say AV1. If the voltage gain of common emitter amplifier is say AV1, if it is AV1 common emitter amplifier, then AV total will be equal to AV total voltage gain will be equal to AV1 into AV2 into AV2. Voltage gain of the common emitter amplifier multiplied by the voltage gain of the common base amplifier. This is the overall voltage gain or the total voltage gain. Now here AV1 is less. AV1 is less, but AV2 is larger value. So very large value. Therefore, what will happen? Total voltage gain will be large. The total voltage gain will be large of the cascode connection. Even though AV1, that is voltage gain of common emitter amplifier, is less, that is compensated by large voltage gain of the common base amplifier AV2, and hence the total voltage gain of the cascode connection is large. Thus, the voltage gain of common emitter stage is very low, whereas a large voltage gain is provided by common base stage. A large voltage gain is provided by common base stage, and hence the overall voltage gain is good, or it is high with the good impedance at the output. Both at the input and output, the impedance is good. High input impedance and high output impedance. These are the features of the cascode connection. Well understood here, students, the cascode amplifier. What will be the circuit in the cascode amplifier? The circuit will be common emitter amplifier. Its output is applied to output of the common emitter amplifier applied to input of the common base amplifier. Okay, this is the cascode connection. Then here there is bypass capacitance. It is CE is there. Here also there is bypass capacitance CB. Input voltage is VI, output voltage V0. Then the supply voltage VCC. Is this understood, students? Cascode connection is clear. Any doubts in this? Cascode connection. Any doubts in this cascode connection? Is it understood? Cascode amplifier. Ankita, is it understood? Ankita?
Yes, sir.
Okay. Rutvik, Gune? Gune?
Yes, sir.
Is it understood, Rutvik? Cascode connection circuit?
Yes. Yes, sir.
Okay, fine. Let us move on to the next circuit. Darlington circuit or Darlington connection. It is also called as Darlington pair. In this Darlington connection or Darlington pair, there are two transistors. Okay, that is why it is called as Darlington pair. There are two transistors. Let us see how these two transistors are connected. The emitter of first transistor is connected to base of the second transistor. Emitter of the first transistor is connected to base of the second transistor. The collector of both the transistors are shorted. What is the connection here? The emitter of first transistor is connected to base of the second transistor. The collector of both the transistors are shorted. Collector of both the transistors are shorted. Okay, so we are getting three terminals here. One is the emitter terminal of the second transistor, base terminal of the first transistor, and the shorted terminal, that is the collector terminal. That means the two transistor circuit will be converted into as if it is a single transistor. The two transistor circuit will be converted as if it is a single transistor it is having one emitter, one base, and one collector. That is, the two transistor or pair of transistor circuit will be converted as if it is a single transistor connection, and hence this connection or this type of circuit is called as Darlington connection or the Darlington pair. In this Darlington connection, so you can see here, Darlington is a very popular connection of two transistors operating as one super beta transistor. So two transistors, they are in composite. Composite means they are connected in this fashion. Emitter of one transistor connected to base of the second transistor. Collector of both the transistors are shorted, and it is taken as a one single terminal, collector terminal. So this is called as the super beta transistor. Super beta transistor. This pair, Darlington pair or Darlington connection, okay, it is also called a super beta transistor. It is a composite transistor connection. Composite means it consists of two transistors, connection of two transistors, and hence it is called as composite transistor connection. That is what it is. The composite transistor acts as a single unit. Then if it is acting like a single transistor, if it acts like a single transistor or a single unit, then its current gain is given by the product of the current gain of the first transistor multiplied by the current gain of the second transistor. What is the current gain of this Darlington connection? The current gain of the Darlington pair or the Darlington connection is the product of the current gain of the first transistor and the multiplied by or and the product of current gain of first transistor and the current gain of the second transistor. That is total beta total or beta Darlington beta D is equal to beta 1 into beta 2. Beta Darlington pair is equal to beta 1, that is current gain of the first transistor, into beta 2, that is current gain of the second transistor. So you can write it like this: beta total beta total is equal to beta 1 into beta 2, beta 1 into beta 2. Okay, this is the total current gain of the Darlington connection. That is, what is current gain, students? How do you define current gain? What is meant by current gain? Voltage gain means output voltage by input voltage. Yes or no? What is current gain? What do you mean by current gain? Or what is the formula for current gain? Yes, anybody? How to define current gain? Ratan? Birje?
Output current by input current.
Output current by input current, exactly. That is the current gain. So beta 1 is the current gain for first transistor and beta 2 is the current gain for the second transistor. If we take the multiplication of these two current gains, that is, if we multiply current gain of first transistor and the current gain of second transistor, then we get the total current gain. Figure shows the Darlington connection, which is also called as Darlington pair. If beta 1 and beta 2, if beta 1 and beta 2 are the current gains of Q1 and Q2, the current gain of Darlington connection is beta square. How I got this beta square? Any guess? How I got this beta square here? Beta Darlington is equal to beta square. Can anybody make a guess? Beta 1 and beta 2 are same. If beta 1 and beta 2 are same, is equal to beta. If beta 1 is equal to beta 2 is equal to beta, then what will be beta total? Beta 1 into beta 2. Here we have written the equation. Beta total is equal to beta 1 into beta 2. Beta 1 is equal to beta 2 is equal to beta. Beta 1 is equal to beta 2 is equal to beta. So if beta 1 is equal to beta 2 is equal to beta, then what will be beta total or beta Darlington pair? It will be beta into
Beta
beta.
square.
Beta square, exactly. Beta into beta, that is beta square. Okay. So that is how we are getting the Darlington pair beta, that is total beta as beta square.
Excuse me, sir.
Yes, please.
Sir, allow Sanket.
Who I have to allow?
Sir, Sanket. He is trying to join. He is unable.
Okay, okay. I'll allow him. Fine, thank you. I have allowed him. Huh? Okay. I have marked his attendance also. Okay. Right. Beta D, beta Darlington is equal to beta square. Beta 1 into beta 2. Beta 1 and beta 2 are same. Therefore, we get beta Darlington is equal to beta square. Now, beta 1 equal to beta 2 equal to 200. Calculate how much will be beta D. Give me the value of beta D. Beta 1 is equal to beta 2 is equal to 200. Tell me the value of beta D. Calculate and tell me. Beta 1 equal to beta 2 equal to 200. How much is beta D? Can calculate manually also. Not necessary to use your calci. How much is beta D? Beta 1 and beta 2 are same. It is 200. How much will be beta D?
40,000, sir.
40,000. Let us see. Let us check. It is 40,000 or some other value. Okay, fine. So beta D is equal to 200 square. Beta 1 and beta 2 are 200. Beta D is equal to beta into beta, that is 200 square. Beta square, so it will be 40,000. Okay, 40,000 is the answer. Right. A Darlington transistor acts as a single transistor with large current gain because the beta value of first transistor will be multiplied with beta value of the second transistor. And the typical value of the beta D, that is Darlington current gain, is in terms of thousands. It is in terms of thousands. Okay. Next, we will see DC biasing of Darlington circuit. This is the basic Darlington connection, whatever we discussed just now, basic Darlington connection. Next, we will move on to DC biasing of the Darlington circuit. What we had studied in module 1, right? DC biasing. Okay. So what is meant by DC biasing, students? Here we are applying DC voltages, right? Capacitors will become open circuit or short circuit in DC biasing. Open circuit. Okay. Capacitors will become open circuit for DC biasing. Therefore, here we are having the VCC, the current flowing through collector is IC, collector current flowing through RB is IB, then the emitter current is IE. Now, can you tell me it is similar to which circuit? Darlington circuit is similar to which circuit? Here, if we look into this circuit, is it having any resemblance? Is it having any similarity with any of the circuit? See, there is emitter resistance. There is emitter resistance. There is base resistance. Let us see that later part. First, we'll analyze this. Okay. So, collector current is there, base current is there, then emitter current is there. Then we are applying the VCC. It is DC voltage. We are applying the VCC. Now, if we apply VCC, now we have to apply the equation to the input portion of the circuit. Input portion is, that is, from VCC, then base to emitter, then emitter to ground. Input portion of the circuit, we have to apply the Kirchhoff's voltage law in order to get the equations. Okay. So let us apply the KVL now. Tell me the KVL equation, students. VCC minus IBRB, positive to negative, minus IBRB, current entering positive, current leaving negative. Then here VBE, VBE is taken as single VBE here. Okay, VB is taken as single VBE because it is acting like a single transistor. Okay, then minus VBE, it is what it is, minus VBE minus IERE, minus IERE is equal to 0. Let us write the equation. So what is the equation, students? We are getting equation is VCC, okay, VCC minus what resistance we are having, RB resistance. So IB RB, base resistance into base current, IB RB minus VBE, base to emitter voltage, minus IERE, emitter current into emitter resistance, that is equal to 0. Real equation. Okay, or here this equation gets modified into, now IE is equal to, what is the equation for IE, students? IE equation, IE is how much? How to find the equation in terms of IB? What we have to substitute here? Yes, anybody? Which equation we have to use for IE? Can anybody recollect? DC analysis. IE is equal to, yes please. IE is equal to, which equation we have to use? If we want this equation in terms of IB, I want the equation for IB. So I have to express IE in terms of which equation, which term? IE is equal to 1 plus yes, beta D, 1 plus beta D, because it's a Darlington. It's a Darlington pair, so it is beta D we are taking, beta D, that is transistor gain, beta D into IB, The equation is IE is equal to 1 plus beta into IB. Okay. As it is Darlington pair, it will be beta D. I is equal to 1 plus beta D into IB. Okay. So this is the equation for IE. Now substitute this equation for IE in the previous equation. That is equation here, this one. VCC minus IBRB minus VBE minus IER is equal to 0. If we substitute in that equation, what we will get? The equation will be VCC minus IBRB, okay, minus VBE. Then substitute this equation, that is 1 plus I is 1 plus beta D into IB, 1 plus beta D into IB. Okay, this is equal to IB. Then one more term is there. I is 1 plus beta into IB, then into RE. RE is also there. That is into RE is equal to 0. Again, simplify this. Now I will take VCC minus VB onto the other side. That is equation will be, I will take VCC minus VBE to the LHS. VCC minus VBE is equal to, VCC minus VB is equal to, I will take IBRB, then this term 1 plus beta D into IBRE to the RHS. VCC minus VBE will be equal to IBRB plus IBRB plus 1 plus beta D, 1 plus beta D into IB, right? IBRB plus 1 plus beta D into IBRE, right? This is the equation that we get. Now in this equation, what is common here in the RHS? IB is common, correct? IB is common in the RHS. Therefore, take IB common. The equation will be, what will be the equation here? Write down the equation. That is VCC minus VBE is equal to, IB is common, base current, this into, what is the equation that we get, students? IB into RB plus 1 plus beta D into RE. RB plus 1 plus beta D into RE. RB, sorry, RB plus 1 plus beta D, 1 plus beta D, beta D into RE, into RE. Okay. Now find out the equation for IB. Rearrange the terms, find the equation for IB. Therefore, we have IB is equal to VCC minus VBE, this divided by VCC minus VB divided by RB plus 1 plus beta D, 1 plus beta D into RE. Okay. Now we got the equation for IB. IB equation is VCC minus VBE, that divided by RB plus 1 plus beta D into RE. Okay. So this is the equation for the base current. This is how we have to find the equation for the base current for all the circuits. For all the circuits, amplifier circuits, this is how we are finding the equation for the base current. Right. So the same equations I have written, applying KVL to base emitter circuit, we are having VCC is equal to IBRB plus VBE plus IERE. IE is 1 plus beta D into IB. Put equation 2 in equation 1 and solve for IB. We get VCC is equal to IBRB plus VBE plus 1 plus beta D into IBRE, or VCC is equal to VBE plus IB into RB plus 1 plus beta D into RE. Okay. VB plus 1 IB into RB plus 1 plus beta D into RE. Then here rearrange for IB. Rearrange for IB here. So take VB to the LHS. We get IB is equal to VCC minus VBE, that divided by RB plus 1 plus beta D into RE. Okay. Now VBE, base to emitter voltage, it is of two transistors, because as it is the connection of two transistors, therefore base to emitter voltage will be almost double. We know that for silicon transistor VB is 0.7 volts, right? But as two transistors are connected, it will be in the range of 1.4 volts to 1.8 volts. That is a typical value of VB for the Darlington pair. That is, it will be in the range of 1.4 volts to 1.8 volts. But getting the point here, then equation for I is 1 plus beta D into IB, that is approximately equal to beta D into IB, because beta D is larger than 1, therefore this will be approximated as simply beta D into IB. I is equal to 1 plus beta D into IB, that is approximately equal to beta D into IB, because beta D is very high. Now what are the DC voltages, other voltages we are having? If you look into this circuit, VE is equal to IE into RE, emitter voltage, that is IE into RE. Emitter current into emitter resistance gives the emitter voltage. And what is VB? Base voltage. If you want base voltage, that is from the base terminal to ground. What is meant by base voltage? Base voltage means from the base terminal to ground terminal. How much is the voltage? That is, it is the sum of VBE and IERE. That is, VB is equal to VBE, base to emitter voltage, plus IERE plus IERE. That will be the voltage between base terminal and the ground terminal. Okay, between base terminal and ground terminal, the voltage is VBE plus IERE. So VB is equal to VBE plus VE, or VB is equal to VBE plus IERE, because VE is IERE. Next, students, Darlington emitter follower. Is this understood, students? DC biasing of Darlington circuit. Any doubts here? Any questions? DC biasing of Darlington circuit is clear. Sania? Shiraj, Shiraj, Shiraj Mujawar. Shraddha, Shraddha, Shubham, Shubham.
Yes, sir. Yes, sir.
Understood, Shubham? DC biasing. Any
Yes, sir.
questions here?
No, sir.
Okay, fine. Let us move on to the next topic. Similar one to the Darlington circuit. Darlington emitter follower. Darlington emitter follower. Now look into this circuit. Look into this circuit and tell me it is similar to which circuit that we have already studied. Okay, in the last class or so we have studied a circuit which is similar to this circuit. Which circuit is that? Yes. Which circuit is that? Look at the name. Darlington emitter follower. Now make a guess. It is similar to which circuit? Yes. It is similar to which circuit? If you look into this circuit, just see, just you should not make a prediction here. You have to see the circuit and tell. See here in between base to collector, RB resistance is connected. RB resistance is connected. Then RE resistance is connected between emitter to ground. There is no collector resistance. And input is applied to base, output is taken from the emitter. Now, can you tell which circuit is this? Input is applied to base, output is applied to emitter. Can you tell me now which circuit is this? Or output is taken from the emitter. Output at emitter follows the input at base. Output at emitter terminal follows the input at base. So it is which circuit? Think. It is which circuit? Output at the emitter follows the input at the base. Which circuit is this? Emitter follower. It is emitter follower circuit. In the emitter follower circuit, what will happen? The output at the emitter terminal is following the input at the base. What is emitter follower circuit? Just we'll go back and see there. This is our emitter follower configuration. We have RB resistance, RE resistance. There is no collector resistance. There is no collector resistance. Input is applied to the base terminal. Output is taken from the emitter terminal. Yes or no? This is emitter follower circuit or emitter follower configuration. Emitter follower amplifier. Okay. Now the circuit what we are studying, Darlington emitter follower, it is nothing but the same circuit. Instead of one transistor, we are having two transistors. Instead of one transistor, we are having two transistors in the connection, connected to each other. Okay. In the form of a Darlington pair. That is the only change. The rest of the connections remain the same. Rest of the connection remains the same. Got the point here, students? So we can see RB resistance is there, then RE resistance is there. Input voltage is applied to base terminal, output voltage is taken from the emitter terminal. Output at the emitter follows the input at the base. This is Darlington emitter follower circuit. It is emitter follower only, but as there are two Darlington transistors or two, it's a combination of two transistors, which is a Darlington pair, and hence this emitter follower is called as the Darlington emitter follower. Note that it is not a basic emitter follower. It is not the basic emitter follower. It is Darlington emitter follower. There are two transistors. The basic emitter follower, there will be only one transistor. But if it is a Darlington emitter follower, then there will be two transistors. Clear here? So the AC input signal Vi is applied to the base terminal. It is applied to the base terminal through coupling capacitance C1, and output is taken through coupling capacitor C2 at the emitter terminal. Output is taken at the emitter terminal through the coupling capacitor C2, V0. AC equivalent circuit of Darlington emitter follower is shown in the next figure. Let us draw the AC equivalent circuit. This is similar to the AC equivalent circuit of the basic emitter follower, right? But here instead of beta RE, we are having RI, input resistance, because there are here it's a combination of two transistors. So combination of two transistors. Therefore, we are having Ri, input resistance. We don't have Re, that small Re. EC resistance will not come here for the Darlington emitter follower because the resistance will be high here. The resistance will be high. It is not EC resistance small Re, but it will be resistance Ri, input resistance small Ri. Okay, because two transistors are connected in this fashion. Okay, Darlington connection. Let us see that. So just see here, this is similar to the emitter follower AC equivalent circuit, almost same. What is the change? The change is here in this portion. In this portion is the change, right? There we are having Re or beta Re here, this one, but here we are having Ri. Okay, as there are two transistors connected, the small value of resistance will not be there, but it will be a larger value. Therefore, we are replacing that Re or beta Re by Ri here for the Darlington emitter follower. This is the only change. Rest of the AC equivalent circuit remains the same as that of the emitter follower circuit, as that of the basic emitter follower circuit. If we see here, this is RB resistance, right? How do you find AC equivalent circuit? If you want AC equivalent circuit, we have to ground the DC voltages, VCC equal to 0. Then capacitors will be short circuit. Capacitors will be short circuit for AC equivalent circuit. So as capacitors are short circuit here, this RB will be connected between base terminal to ground. VCC is 0. RB will be connected between base terminal to ground. That is what is drawn here, between base terminal to ground, RB. Okay. Then next, conductor will come. Next will take this portion, Ri. Next will be Ri between base to emitter. Base to emitter Ri, input resistance Ri. That is Ri here, base to emitter Ri we have. Then here at the junction we are having, this resistance Re, emitter resistance here. This is Ri between base to emitter, and when it comes here, it is Re, this resistance. Re is also there, emitter resistance. So that will also be coming in the AC equivalent circuit, capital Re, emitter resistance. This is Re here, that is between the junction and the ground. Then what else we are having? We are having collector current flowing. This is beta IB. IC is equal to beta IB, or here it will be beta D into IB because it's a Darlington connection. It will be IC is equal to beta D into IB. Current, that is controlled current source, beta D into IB. Okay, this is the same, everything is same as that of the basic emitter follower, only instead of Re resistance here we are having Ri. Okay, that is the only change. Input current is II, input voltage is Vi, and output voltage is taken across emitter resistance Re, output current is I0. Just see here, output current is I0, it is flowing into the emitter terminal. Here input current is flowing into the base terminal according to the convention of the two-port network. And this is emitter current IE, this is collector current IC. So IE is equal to IB plus IC. Okay, this is the AC equivalent circuit of the Darlington emitter follower. Let us go back and see AC equivalent circuit of the basic emitter follower, how it is same. Just here it is Ri here. Let us see what is there in basic emitter follower circuit AC equivalent. Here it is beta Re. In the emitter follower, it is beta into Re, AC resistance. Okay, but here for the Darlington emitter follower, we'll get Ri. Okay, so while studying, just we have to look at these changes, how that it is different from the previous circuit. Okay, or how it is different from the basic circuit. What are the changes? We have to see these things and we have to study while studying. Okay, so it will be easy to remember if we study in this way by comparing how it is different from the previous circuit. Okay, what are the changes, or how the circuit is different from the basic circuit? What are the changes in the AC equivalent circuit? Okay, or what are the changes in the parameters? What may be the changes in the equations? Okay, just we have to remember like this. It becomes easy for us to. It becomes easy for one to remember the things. Okay. In today's class, students, we started with the cascode connection, right? Which is the common emitter amplifier output applied to input of the common base circuit. Then next, we took up Darlington connection, in which the emitter of one transistor is connected to base of another transistor. The collector of two transistors are shorted. This will be converted into a single transistor connection. This is called as Darlington connection or Darlington pair. There are two transistors, hence it is called as Darlington pair or Darlington connection. The total current gain will be the product of the current gain of individual transistors, that is beta 1 into beta 2. If the two current gains are identical or they are same, then beta D will be beta square. This is DC biasing of Darlington circuit. We applied the KVL equation to the input side, to the input portion of the circuit, that is from collector to base emitter, then emitter to ground. Then after applying the DC analysis, we got the equations for, that is base current. Base current equation is VCC minus VB divided by RB plus 1 plus beta D into RE. Then VE is equal to IE RE. VE is equal to IE RE. Then VB is equal to VBE plus VE. Then later we took up the Darlington emitter follower circuit, which is similar to the basic emitter follower, but here we are having two transistors instead of a single transistor. Then later we saw the AC equivalent circuit of the Darlington emitter follower. It is similar to the AC equivalent of basic emitter follower. In the basic emitter follower, the resistance here is beta Re, but here we are having small Ri, that is input resistance of the Darlington transistors, that is base to emitter resistance, input resistance of the Darlington transistors, Ri. Rest of the AC current circuit is same. Here we are having beta D into IB. There it is only beta IB in basic emitter follower. In Darlington emitter follower, it is beta D into IB. It is current gain of the Darlington connection. Okay, beta D into IB. Right. So students, this were the topic in today's class. Any questions here, students? Any doubts? Manjunath, any doubts? Manjunath, Rajat, Rajat, Gaonkar Rajat Ramchandra, Vivek, Vivek, any doubts here, Vivek? Tejas, Tejas,
Yes.
any doubts, Tejas?
No, sir.
Any problem in understanding?
No, sir. Understood, sir.
Fine. Suraya Banu, Suraya Banu,
Yes, sir.
is it clear, Suraya Banu?
Yes, sir.
Right. Shraddha, Shraddha, Munshal,
Yes, sir.
is it clear, Shraddha, today's topics?
Yes, sir.
Any questions here, Shraddha?
No, sir. No doubts.
Okay, fine. Sanket, Sanket,
Yes, sir.
was the topics clear, understood?
Yes, sir. Clear, sir.
Just go through those starting topics. If you have any doubts, you can ask me.
Yes, sir. Connected a bit late, sir.
Okay, fine, fine. Okay. Sanjay, Sanjay, Sania, Sania,
Yes, sir.
Sania. Was it clear, Sania?
Yes, sir.
Any questions, Sania?
No, sir. No questions.
Okay, fine. Sai Prakash, Sai
Yes,
Prakash.
sir. Yes,
Was
sir.
it understood, Sai Prakash, that today's
Yes,
concepts, topics?
yes, sir.
Right. Sagar, Sagar, Sadashiv, Sadashiv, Rutvik, Gune, Gune,
Yes, sir.
Understood the today's topics, Rutvik?
Yes, sir.
Okay, fine. Ramesh, Kirti Patil, Janvi,
Yes, sir.
understood today's topics, Janvi?
Yes, sir.
Okay. Any questions?
No, sir.
Right. Ankita,
Yes, sir.
any problem in understanding, Ankita?
No, sir.
Any doubts?
No, sir. No doubts.
Okay, fine. Then in the next class, we will continue with the next subsequent topics. Okay, that we'll see in the next class. Okay, I'll be continuing with the analysis of the that is a Darlington emitter follower. That analysis will take up in the next class. Performance parameters. Okay, thank you.